all of the internal angles are the same. Alright, so for this, alright, for any of these, you don't need calculus to find the area of, except for something really crazy like this. So if you're given the locations of the vertices, 1, 2, 3, 4, 5, 6, 7, 8, 9. So you're given the location of all these vertices all the way around. It turns out that there is a surprisingly nice formula for computing the area of even a polygon as crazy as this. And this is where calculus is needed. And see, it was tempting to already violate the red bars here, go to the other side of the board, but I'll resist doing that. Okay. It's a reflex. Yeah. So yeah. I'm gonna once had a televised class where I needed to stay on one side of a room, so I'll just imagine I'm back there again. All right. So let's suppose that we'll call the polygon P. Now, based on what you are familiar with, and how would you go about computing the area of something like this? How could you even attempt it?
You could break it up into simpler.
Yeah, you break it up into triangles. What would you do with each of the triangles? If this is all the information you have, just location of the vertices. Yeah, it can be done. And you could try simple integrals, because for each, you can decompose this into triangles. And get the area that way. All right, that's doable. But now imagine you want to try to find a formula.
So do anyone.
Yes, that's taking this approach with any kind of triangulation, and there's more than one triangulation. That's a tall order. But using the fact that the area can be written as a double integral over P of this function f of x y equals 1 dA, we could actually come up with a nice and memorable whatever.
Memorizable, easily remembered.
Sure. Formula for the area of any polygon whatsoever. All right. So by the time we get to the end of today, yes.
So when you say you're given the points,
yeah,
does that tell which points are connected to which points as well?
Yes. So you can assume that you're given them in order.
Okay.
Yeah, you know what the order is. Yeah. So 1, 2, 3, 4, 5, 6, 7, 8. Here's point number 9, so you assume that point 9 also connects to point number 1. Mm-hmm. Yeah. So you have the cyclic ordering of the vertices, and that's all you know. So in order to figure out something like that, we're going to be using a theorem that is a real subject of today's lecture called Green's theorem. All right. Okay. Now, Green's theorem stems from trying to compute line integrals that we've been talking about lately, where C is a closed curve, and I'm going to give it a few other properties too. It's also going to be called a simple closed curve. In other words, it does not intersect itself. And we're also going to say that it has positive orientation. Which means you traverse it counterclockwise. Of course, counterclockwise can be a little difficult to figure out if your curve is going like this. All right. Depending on where you are on the curve. But the idea is, as you traverse the curve, one thing that you might notice is the region, the interior of the region D that's contained within the curve C is on the left. So picture a little person walking along the curve, the region is going to be to their left as they're facing in the direction that they're walking. So we're going to assume that any curves we deal with are going to have this positive orientation. That's important because, as we've seen, when you change the orientation of the curve, the sign of the integral, the line integral over the curve changes. All right. Now, if the vector field F happens to be a conservative vector field, and we have a closed curve like this, we already know what this integral is. What is it? That's what we talked about last time. Only if F is conservative.
0?
Yeah, it turns out to be 0. Because you apply the fundamental theorem of line integrals, you're evaluating function little f at the same point, and subtracting them, you get 0. But if this is not conservative, then you got some work to do. And if you try to evaluate this line integral in the usual way, for a case where you cannot apply the fundamental theorem of line integrals, and you end up doing this, well, the problem could come up, this simply might be too difficult to do. Now, we may not agree on what an appropriate threshold is for, well, once you set up this integral, whether it's too hard to do or not. But that aside, it is possible to rewrite this in an integral that may be easier. Okay, so what we're going to do is we're going to assume that this closed curve encloses a simple region D, and by simple I mean it's a region of type 1 and type 2 at the same time. Now, the convenience of that is that we can define a region in two different ways. Now, it's been a while since we talked about what it means for a region to be of type 1 or type 2. So to refresh your memory, we can define D this way: set of all points such that X is between A and B, and Y is bounded by two functions of X. So this is a region of type 1. Or we can look at this region of type 2, where Y is bounded by constants and X is bounded by functions of Y. Okay. So, depending on what we're trying to integrate, either point of view could be most convenient. Any triangle generally can be looked at as a region of type 1 and type 2. Or a region that's triangle except maybe it has some curved boundaries. For instance, something like this. We've done at least one example involving a region like this. So you can look at that, a region like that, as being of type 1 and type 2, whichever is more convenient. Okay. So we're going to look at the problem of how you evaluate an integral like this when C is a closed curve and it's a region like this. Okay. Now, we'll assume that f is